Ladies and gentlemen, distinguished guests, my name is Paul Beal, Professor of Physics and Chair of the George Gamow Memorial Lecture Committee. We welcome to the 52nd George Gamow Memorial Lecture. This public lecture series honors George Gamow, a professor of physics at the University of Colorado from 1956 until his passing in 1968. The Gamow Memorial Lectures were initiated in 1971 by the Department of Physics, and in 1975, Professor Gamow's wife, Barbara, left a bequest to the university, establishing an endowment for the purpose of maintaining these free public science lectures in perpetuity. All subsequent lectures have been supported by this generous gift. I would like to thank Igor and Elfriede Gamow for their continuing support for this wonderful program and for establishing an undergraduate physics scholarship in their names. The first Igor and Elfriede Gamow Scholarship recipient, Max Ruth, is sitting with them in the front row. We have many distinguished guests here tonight, but please let me introduce three of CEO's Nobel laureates. Professor Thomas Cech, 1989 Nobel Prize in Chemistry. Professor Eric Cornell, 2001 Nobel Prize in Physics. Professor Jan Hall, 2005 Nobel Prize in Physics. I'd like to thank you and all of the other people who have helped the University of Colorado become the great success it is. Our students, staff, faculty, alumni, the citizens of Colorado, and our generous donors. George Gamow was a giant in the history of science. He made seminal contributions to nuclear physics, astrophysics, and molecular biology. He was also an excellent teacher and a prolific writer. George was born in Odessa in the Ukraine in 1904. In 1928, at the age of 24, Professor Gamow was the first to apply quantum mechanics to explain the properties of radioactive alpha decay. This was only 2 years after Heisenberg and Schrödinger had used quantum mechanics to explain the atomic structure of hydrogen. In the same period, he developed theories of the thermonuclear reactions that power the sun and other stars, and first proposed the nuclear drop model that became instrumental in the theory of nuclear fission. George and his wife, Rose, defected to the West in 1933 after attending the famous Solvay conference that brought the greatest minds in physics together to discuss radioactivity and nuclear physics. Other attendees included Einstein, Curie, Rutherford, de Broglie, Bohr, Schrödinger, Heisenberg, Pauli, Dirac, Fermi, Meitner, and many other leading physicists. In the 1930s, George's work with Edward Teller was instrumental in the development of the theory of radioactive beta decay. In the 1940s, George and graduate student Ralph Alpher published a landmark paper about the origin of the light chemical elements in the Big Bang. This work occurred in an era when the idea that the universe had begun abruptly was still controversial, yet Gamow and Alpher produced the first quantitative predictions based on the fundamental physics that follows from Edwin Hubble's observation that the universe is expanding. This paper was published on April 1st, 1948. Perhaps not coincidentally, George added, always the whimsical jester, he added his friend Hans Bethe's name to the paper as a pun on the Greek alphabet. The paper is widely known as the Alpha Beta Gamow theory of primordial nucleosynthesis. In the mid-1950s, George turned his mind to explaining the genetic code. Many members of the interdisciplinary RNA tie club that George formed became scientific leaders in unraveling the mysteries of DNA. George was the first to show that a 3-letter nucleotide code was sufficient to define all of the known amino acids. George was a prolific writer. His many successful books explained even the most arcane concepts of science and mathematics to budding scientists and the general public. I still have the copy of 1, 2, 3 Infinity that my parents bought for me when I was in junior high school. It is dedicated to and kindly autographed by his son Igor, who wanted to be a cowboy. In 1975, George's widow, Barbara Perky Gamow, left a bequest to the university to permanently fund this public lecture series to honor George. The Gamow Memorial Lecture Endowment stipulates that the Gamow lecturer, quote, shall be a person widely known for scholarly achievement in one or more of the fields of physics, astrophysics, mathematics, biology, chemistry, geology, or engineering, and shall be known for his or her excellence in interpreting science for the general public. Our speaker tonight is a perfect example of what Perky envisioned. It's my honor to introduce Professor Philip Weiser, who will introduce tonight's speaker. Phil's distinguished career includes serving as a law clerk for 2 U.S. Supreme Court justices, CU alum Byron Whizzer White and Ruth Bader Ginsburg. Phil served in 2 U.S. presidential administrations as senior counsel to the Assistant Attorney General and Deputy Assistant Attorney General. Phil is the Dale N. Hatfield Professor of Law and Telecommunications and Executive Director and founder of the Silicon Flatiron Center for Law, Technology, and Entrepreneurship, and he served as the Dean of the University of Colorado School of Law from 2011 to 2016. Ladies and gentlemen, Phil Weiser.
Thank you, Paul, for that very kind introduction. I have to say, introducing Vint Cerf is one of the harder assignments. I can imagine that's coming from someone who is dean of a law school. But Dale Hatfield asked me to do this, and I can't say no to Dale Hatfield. What many of you may know is that in the world of telecommunications and internet policy, Dale Hatfield and Vint Cerf are akin to 2 members of the Justice League, for those cartoon fans among you. I would also leave it to you to figure out which characters they are and who else is in that pantheon. I thankfully could research Vint using the internet because of his accomplishments. In fact, when I mentioned to Vint I'd be introducing him, he said, well, just Google it. You'll find all you need to know. In full disclosure, I did rely heavily on Wikipedia for this introduction. This particular week is one that we can and should treasure, leaders like Vint and Dale, because of the passing of John Perry Barlow, who was a leading force on internet policy, founding the Electronic Frontier Foundation, and was actually called the Poet Laureate of cyberspace. Like Vint, John had a real way with words, and in fact once quoted Vint in his battle against the ITU for control of the internet as saying, this breed of dinosaurs hadn't figured out that they're dead yet. I'll come back to that. From a current standpoint, it's not easy to appreciate just how impactful Vint Cerf is as a historical figure and a leader. To me, he's a legend. He's an inspiration and a true innovator. He started out as a professor of computer science, and he worked with Bob Kahn to design and implement the Transmission Control Protocol and Internet Protocol, commonly known as TCP/IP, which forms the basis of the internet. On account of this invention, our world was changed forever, and Vint won the Turing Award among many other honors for this accomplishment. What makes Vint so special is not only that he's one of the internet's founding fathers, but that he's continued to provide critical leadership to help the internet develop as a thriving global medium, building institutions, stewarding its development, and engaging in important policy discussions. To take a couple examples, he was a founder of the Internet Society, which oversees the Internet Engineering Task Force. He also is critical in supporting the development of the institution known as ICANN, the Internet Corporation for Assigned Numbers and Names, and he served as the board chair of that body from 2000 to 2007. If it were up to established forces, we would not have the internet. People at AT&T reportedly said, it will never work, and if it does, it will destroy us. They were right about the second. Part of what Vint and others saw was that the internet's open architecture that allowed innovation without permission was essential to unforeseeable technological changes. What Vint also helped to do is develop a new model of governance. It's often called multi-stakeholder governance. And if people want to learn more about that, there's a law school conference tomorrow and Monday that I would encourage you to join us at. And finally, I want to acknowledge Vint's moral courage and his leadership addressing challenges that we face today raised by the internet, including issues around access for those with disabilities, gender equality, and international access to the internet. Vint has been a fervent advocate on all fronts, caring about people for whom technological change was not necessarily their friend. Vint also is a true visionary, and whatever he has to say today, pay close attention. When people laughed at the idea of the Internet of Things, Vint called it everything over IP, Vint was right. And when people laugh at his plan for an interplanetary internet, I wouldn't be so sure, because I'm not going to bet against Vint on anything. And without further ado, let me introduce Vint Cerf.
Thank you. You know, when people clap before you've said anything, it's probably you should just sit down because it won't get any better than that. So, Phil, thank you very much. Of all the introductions I've had, that was the most recent. Let me begin by thanking the Gamow family for incredible hospitality. We had a lovely dinner reception a little while ago, and certainly their generosity makes it possible for these lectures to happen. And of course, I want to thank the Gamow committee for deciding that I could be your lecturer tonight. I have to confess to you, having heard about who some of the other Gamow lecturers are, like Jane Goodall and Brian Greene, I'm feeling a little uncertain up here about my ability to respond to the level of their excellence. And to say nothing about the terrible weather, I mean, I'm not even sure I would have come out in this weather to listen to me. So I appreciate very much your willingness to join us tonight. This is not the slides that I want. Does somebody want to help me find, or is this, let's see. Yes, we're good, all right. I was afraid I was gonna have to log in and convince this machine I'm me. So what I would like to do tonight is to raise a significant problem without a lot of solutions. There will be a few ideas that I want to share with you tonight about the solution to these problems, but more important, I think, especially for people who are here who have interest in solving hard technical, legal, and let's say business model problems, I hope that this will set you off to thinking and maybe some solutions will emerge over time. So I want to start out by reminding you about how we store our information, our knowledge, because learning to write was probably one of the most important of the inventions of the human race. The ability to store things for the future, for people to communicate with the future, or for the future to communicate with the past. And so you will recall that there are various ways in which written material can be captured and stored for long periods of time. Cuneiform tablets coming from several, 4,000 years ago from the Babylonian and Assyrian periods. These tablets were usually not intended to last for very long. There were clay tablets. They were often used simply to record inventory in a warehouse. But some of the warehouses burned down and baked the tablets, and they became literally hard as rock. And they have lasted for thousands of years. And if you can still read cuneiform, which a small number of people can, these communications are still available to us thousands of years later. Papyrus is another medium in which writing has been recorded. It in itself is not a very resilient kind of recording material. But if those scrolls that were written were kept in a very dry space, as the Nag Hammadi scrolls were, or the Qumran scrolls were. They can last for quite a long time. And so we have evidence of writings from several thousand years ago that we still have access to. Vellum, which is sheepskin or goatskin, is actually an extremely resilient material, and so many things were written down on vellum, and they are still available to us today. Many of those things were illuminated, they were colored with various things, including gold ink. And some of these things are as beautiful and as striking today as they were 2,000 years ago when they were first written. We also have things like a paper with rag content, which has also lasted for quite a long time. This is paper that would have been used in the 14th, 15th, 16th, and 17th centuries, 18th centuries, with a large amount of rag content in it, so not too much sulfur, and therefore this lasted a long time. I was looking at books from the 14 and 1500s over the weekend, and some of them looked like they had been printed yesterday. The quality was so good. Now, with the 1800s, the 19th century, of course, people invented paper made out of tree bark, pulp, tree pulp, wood pulp. And this involved a fair amount of processing, chemical processing that included sulfur. And the result is a very cheap but very poor quality material. And so books written on that kind of, or printed on that material haven't lasted nearly as long. If you haven't noticed a kind of trend, you can see that the oldest materials had the longest lifetimes, and the more recent materials have lasted less and less time, until finally we get to these kinds of writing materials, magnetic discs and optical discs. They don't have a very long lifetime at all. Some of you may still have 3.5-inch floppy disks or 5.25-inch floppy disks, or maybe VHS tapes, but you may not have any readers that can still read them. And later I'll be telling you about a place that has some, which I discovered only this morning on the campus, so this is an important discovery for me. But I have to say that these magnetic media or optical media, while they are touted as high density and wondrous new things, have not shown very much lifetime. And even if the bits are still there, finding something that can read the bits is a significant challenge. So here we are in the 21st century with writing media that don't have very long lifetimes. So we also recognize that we are creating substantial amounts of content today, most of it static in character. So things like YouTube, although those are videos, are really sequences of static images. And so you could think of them as static recordings, or Flickr, the pictures and things like that, or Google Photos. But there is a different problem arising in the context of materials that require execution of software. So I want you to think for just a moment that about a book that some of you I hope have read, and if you haven't, I would recommend it, and that's Doris Kearns Goodwin's book, The Team of Rivals, which is all about Abraham Lincoln hiring his opponents for the presidency to be part of his cabinet. Now, if you read this book, you see and read dialogue which feels and sounds very authentic. But we know that Doris Kearns Goodwin was not around in the 1860s. So one of the questions is, how could she have reproduced this dialogue so faithfully? And the answer is, she didn't just make it up. She went to libraries around the world and archives, or at least around the US, and got the letters of the principals to see what they were saying to each other, what topics they were talking about, how they were expressing themselves, what positions they took. And from that source material, she was able to reproduce very credible dialogue about the issues of the day. So now I want you to imagine that you are a 22nd century Doris Kearns Goodwin, and you want to write about the first opening decades of the 21st century. What access would she have to our communications? Would all the emails still be around? What about the tweets? What about the blogs? Now, some people would, and the web pages for that matter. Now, some people would say, well, maybe it's just as well that none of that survived into the 22nd century. But historians will tell you that it's important to know what happened. What were the dialogues of the time? What were the issues and the problems, things that people debated? And it isn't clear that all of these electronic exchanges will survive in any useful form over 100 years. And so this is part of the problem that I'm putting before you tonight, is this digital dark age, which is not unlike the Middle Ages when, especially in Western Europe, the sort of the lamp of learning went out, except for the monks in the monasteries who were copying older writings onto new vellum, for example, in order to preserve that information. And in fact, the Islamic cultures also, in parallel, were recording some of the Greek writings and the Roman writings for preservation as well. So here we are with this very ephemeral kind of communication with an uncertain future. Now, here's the problem that is very difficult to deal with, and that's digital objects that are executable. You have to have a computer in order to do anything with the bits to make sense of them. So computer games, for example. But there are other applications that you might use every day, like documents that you would create using applications like Microsoft Word or Google Docs or other things, or spreadsheets or presentations and the like. All of the bits that are associated with these objects require a computer and some software in order to render the objects and to allow for interaction, a spreadsheet, for example. And so this gets now more difficult than simply preserving bits. We also have to find a way to execute the software that makes the bits meaningful. And that software, that application software, typically runs on an operating system of some kind, which runs on top of a piece of hardware, a laptop, a desktop, maybe something in the cloud. The question is, will those operating systems still be available 50 years or 100 years from now? Will we be able to run the applications? Will the hardware be around? And my general answer has been no, except for discovering a laboratory near the campus that actually has some very old equipment that's still operating, much to my astonishment. But I think the general observation that these devices will not last forever is relevant. And so the ability to do something useful with executable content over a period of 100 years is still very much in question. Well, just to give you a sense for the quantity of digital content that's being generated, this is an example of content that's being generated per minute or per day or per year. And I don't propose to go through every single one of these items, but just look at these numbers. I mean, YouTube gets 400 hours of video per minute uploaded into the system. We recently had a 1 billion-hour watching day, a day where 1 billion hours of video were watched by the people who were part of the YouTube community. There are millions of searches per minute on Google. There's a number which I am still not quite sure I believe. Americans use 2.66 petabytes per minute of data. And I'm not sure exactly what that statistic means, but we could go to webassets.domo.com and find out exactly how that metric was composed. But the thing I want to emphasize is that we as a community and online world are generating enormous amounts of digital content. 1.7 trillion photos were estimated to have been taken just in the last year alone. And so a lot of people, including you and me, probably imagine that all that content is just out there. It's sitting in the cloud. It's sitting in our home computers on hard disks or little memory sticks. And we don't think that they would ever go away. I mean, the bits are ethereal somehow, but they're actually realized in a physical object, and those physical objects have finite lifetimes. So this idea of preserving digital content, in my view, is very, very important. It's a really broad and complex topic. It's not just a question of copying the bits into a new medium. We have a bunch of other things to worry about. What's the structure of the data that's in those digital objects so that we can write software to understand what that content means. How do I render it? How do I interact with it? How do we even point to the content? Now, lots of you who use the World Wide Web are very comfortable with the notion of a universal resource locator, a URL. Embedded in the URL is something called a domain name, something that ends in .com or .net or .org and so on. In fact, there are a couple of thousand top-level domains currently in existence. Some of them are country codes like .fr, .de, .us. What you should understand, though, is that domain names are not stable identifiers. And the reason for this is there is a business model behind the domain name system. You have to keep paying registration fees every year in order to keep that domain alive and convertible into an internet address, because that's how the internet works. The URLs and the domain names are looked up in a distributed directory and translated into a numerical address, which then lets you get to the correct destination in order to find the object that this reference points to. If you fail to pay your rent, the domain name no longer is registered and it doesn't resolve. And so that means anything that's pointed to by a URL, including printed materials in scientific documents, won't resolve, and so the reference won't be discoverable. To make matters worse, sometimes a domain name which is expired is re-entered into the population of live domain names because somebody purchased the domain name. Now it may resolve again, but it may resolve to a destination that wasn't intended by the party who used it in the first place. So these are unstable identifiers. We don't have, but need to have, a regime in which the identifiers for digital objects are stable over really long periods of time. And my colleague, Bob Kahn, introduced the digital object architecture some time ago. We started working on it almost 30 years ago. It's now in operation and is used by a number of scientific publications, by the music industry and others, to provide permanent references that don't have the same unstable property that domain names have. If we're going to build an archive that is accumulating digital content, we're going to have some standards for what information is required to bring into that archive. It's not just the bits that need to go in there, but it's all the metadata. Where did it come from? What is its origin? What is this about? Are there any access controls? Are there any intellectual property constraints? A whole variety of metadata about provenance and structure and meaning have to be included with the actual bits of these objects. Otherwise, we won't know what to do with them. And in particular, if there are constraints on who should have access to the information until, for example, a certain time expires, that information has to be part of the archive as well. Now, it turns out, as we will find a little bit later in this talk, that there are legal frameworks that are needed in order to give power to organizations that are acting to preserve digital content. They probably have to have some privileges that we wouldn't ordinarily have. For example, they have to be able to get access to executable code, and they have to be able to keep that. They have to be able to allow other people to have access to that executable code in order to render objects that that application software was used to create. And that may extend beyond the normal privileges that you and I might have as ordinary users. And then there's this long-term question. If we're going to store digital content over hundreds of years, the question is, what's the business model that sustains that ability to keep the archive going, to continue ingesting new material, for continuing to copy the digital information from one medium to the new media as time goes on? There has to be a financial support model for that. So these are the kinds of things that have to be resolved in order to achieve successful long-term digital preservation, and I submit to you that those problems have not yet been fully resolved. These are examples of challenges, some of which are reminders of the previous slide, but you have to copy the bits to new media because old media won't last forever, the readers won't last forever. The metadata has to be captured. This notion of digital X-ray is interesting. Think about what happens when you are running a program on your laptop. Several things are happening at the same time. There is the digital object you're creating, the document or the presentation or the spreadsheet. Then there is the program that's helping you do that, like Microsoft Word or Excel or something like that, or maybe something up in the cloud. Then there's the operating system that hosts that application. All of that's running in your laptop or your desktop. And then the hardware underneath is interpreting all of the instructions that the operating system and the application are asking the hardware to perform. In order to capture the state of that whole ensemble, you kind of want a digital X-ray machine that takes a digital snapshot of the hardware and its instruction set, the operating system, the application, and the object that you're dealing with. And if you could take that little X-ray and capture it and put it away somewhere, then in theory, you could take that collection and put it back into an environment where you could execute all that code and you'd recover the digital object that you had stored away, like the spreadsheet or what have you. Of course, this is a fanciful idea. We don't have digital X-rays, so we have to design and build a system that has the same effect. There are issues about what happens to software that you don't own. In fact, a lot of companies that provide you with software say you only have a license to that software to use it, but you don't own the software, even if you bought the disk that has the software on it. When companies go bankrupt, bankruptcy laws are really funny little objects because they basically say any asset that's owned by the bankrupt company is potentially an asset to be sold in order to pay off the bondholders of the bankrupt company. And so bankruptcy courts and bankruptcy laws tend to treat just about anything as a potential asset. So let's imagine that the company that made the application software that you are depending on for a bunch of objects that you created has gone bankrupt. And you say, well, can I have the source code so that I can make sure that I can still get to my digital objects that I've created with that software? And the bankruptcy court may say, of course not. That's going to be sold to the highest bidder. Or you might say, well, can I have just the object code? And they may say, no, part of that code is part of the assets that we're going to sell. The same argument could be made for the operating systems or even the hardware. So there's a real problem that you and I have, having invested in using these tools to create content, where a situation arises where we don't have our ability to retain a capacity to use and build and manipulate. So intellectual property rights are a similar issue. If a company goes out of business and you say, can I have the source code? And they say, no, it's still under patent. And if you're not in a position to buy the patent rights or pay for license fees, you may be out of luck trying to preserve the utility of the information you created. There's also a question about how many different places store this stuff away. And imagine that there are multiple parties who recognize this problem and undertake to store away digital content. Then the question is whether these archives are capable of interworking with each other. And one argument might be, who cares? You go to whichever one you need to get to the content. But if an archive goes out of business, you would like to be able to move the data that's in the archive to another one. And to achieve that, you want interworking among these various archives. That calls for standards, which in many cases have yet to be developed. So this is some of the challenges that we have. Now here's a breaking news example of this problem. Just this month in February, the NASA image satellite, which was lost in 2005 and declared dead in 2007, was discovered by an amateur astronomer. They detected the signal from this satellite, which NASA thought was gone and dead. And they were able to identify which satellite it was because part of the telemetry data said this satellite had ID number 166, and that is the image satellite in the NASA catalog. So NASA made use of its deep space network, these are big 70-meter dishes, to capture the signal from the image satellite and verify that it's actually operating. So the problem that they ran into is that now they would like to validate the state of the satellite and start gathering data back. Except there's this little problem. All the software for this satellite had been recorded on a 4mm tape cassette for which NASA had no active reader. And so now they got this little cassette with all the information on it they need, and they can't read it. Except ESA, the European Space Agency, has a 20-year-old project which just happened to use the 4mm cassette format, and they still have a reader that works. And so by sheer luck, NASA now has the potential to recover information from the long-lost satellite. Look, this is what's called preservation by accident. This is not a plan. And so part of my object in today's talk is to say we need a plan for preserving digital information over long periods of time, and we don't have one yet. Well, there is one example, and this doesn't solve everything. It's an example of something that can be done because it was demonstrated by a team at Carnegie Mellon. Mahadev Satyanarayanan, I practiced really hard to say that, whom we call Satya for obvious reasons, was the one who led this NSF-sponsored project. And his idea was to simulate old hardware on new hardware so that you could load old operating systems and load old applications and run the application in this simulated virtual environment. And by that means, be able to interact with old objects that have been created by that software. So they set about to emulate old hardware and to run the various programs that otherwise would never be able to run again. So this is why I warned our interpreters that I was going to get into geeky part of the discussion tonight. I'll try hard not to get too deep into this. But I want you to appreciate that this is not easy. There are lots of different things that you have to accomplish, you have to achieve in order to successfully run a virtual emulation of an old piece of hardware, successfully running the software that had been written for it. And although some of these things are fairly complex and specific, you can appreciate why they might be important. For example, which languages, literally which spoken languages or written languages are associated with this particular application? What about time zone settings, which might be important? What about the details of the hardware instruction set that has to be emulated? And I have to tell you that one of the more amusing but kind of frustrating aspects of all this is that sometimes hardware doesn't always work the way it was supposed to. There are bugs in the hardware just like there's bugs in the software. And there are times when programmers, when they find out about the bugs in the hardware, take advantage of the bugs in order to write their software. So if you're going to emulate this old piece of hardware, you have to emulate the bugs in the hardware too in order to get the software to work. I mean, it's these little nuances that can really get you if you're trying to make the simulation work. So this is sort of the digital X-ray idea, where you capture all this information in order to achieve a simulation. Now, these guys recognize that emulations of hardware that can run these old software programs actually take up a lot of space. I mean, it's a honking big pile of bits, that's a technical term, in order to successfully run the emulation. And so they were actually trying to figure out a way to have a simulation program partly running in the local machine and partly being pulled in at the right time. So instructions being pulled in from the outside, from the cloud, for example, in order to sequentially execute this emulation without having to put all of it in one place all at the same time. So they literally looked at YouTube and said, well, let's see, how YouTube works is that you don't have the whole movie loaded in your machine. What you get is the next frames as they are needed. And so the idea of doing this streaming by prefetching as needed was the idea, except for one problem. When you're executing software, it doesn't execute in a nice sequence like a movie playing back. It hops around. in the instructions. And so you have to keep making sure that you've got the right software inside the machine at the right time in order to execute without stopping and waiting for something to be uploaded. So they basically built a system that had an emulation capability, very low-level emulation capability in the client machine. And that client emulation capability would pull in all the information that it needs from the outside in order to run the simulation. So it would simulate the hardware, or emulate the hardware, and then it would run the operating system that it had loaded in, and then it would load in the application, then it would load in the digital object. And they successfully demonstrated a variety of fairly old systems going all the way back into the 1980s by emulating the old hardware from IBM or from Apple or from other companies. And they did this for something like a half a dozen different systems to show it was feasible to do that. So this again is sort of the way they packaged everything up. Is this basic software running in the local machine that you're going to use with bits and pieces of the information that are required in order to create a successful emulation. And the digital Xray process captures everything that you need to know about this virtual environment and then writes it out as this giant file, and that's stored away. So that's the digital Xray. And then when it's time to actually run the program that had been saved that you need to use, you pull all of this stuff in on a dynamic basis as needed in order to execute the old program. Well, without going into too much more geeky detail, it turns out that this is non-trivial. As I said before, the reference patterns for what do I execute next don't come in a serial fashion. So you have to prefetch things and hope that you're getting everything you need in order to continue the execution instead of having to wait to pull in yet another page of information in order to keep the execution going. So they ended up doing a kind of demand paging operation where whenever the machine needed something, it asked for it, and it tried very hard to load things ahead of time if it could figure it out that they would be needed in the future. I have to tell you, one of the side effects of this emulation process is that the newer machines that were used to emulate the older machines often ran faster, even under emulation, than the original machines did. The result of this is that when you were playing an old video game on the emulated hardware, the machine ran too fast, and they had to artificially slow it down. Otherwise, you couldn't play the game because the machine was always running ahead of you. And so one of the examples of I have to actually slow the clock down to 1980 speeds in order to make the 2018 version of the emulated system work. So this is a huge challenge, but they overcame it successfully. They even managed to organize an implementation of this so that all the emulation took place in the cloud, and the only thing they had on the local machine was a presentation of what the program was doing at the moment and showing on the screen. So you can see how this notion of emulation migrated from doing it on a local machine to doing it out in the cloud. And this, by the way, is a pretty important notion as you start thinking about long-term preservation. To the extent that the clouds will be around for a while, and I work at Google and we hope the clouds will be there for a long time, then you can run all kinds of different emulations in the cloud. And those can be maintained over long periods of time by the cloud operators, added as time goes on, as new machines are developed, as new hardware is developed, as new operating systems are developed, as new applications are developed. They can all be deposited in the cloud and called upon on demand in order to run old software. So if you have an old file that we've been able to retrieve, maybe from a 5 1/4-inch floppy disk, you might be able to upload that particular digital object into the cloud, put it into the appropriate environment to emulate the old hardware and software, and then be able to recover access to that object. So this is a fairly powerful theme, which might actually be part of the story for solving this digital dark age problem. Well, we're a long way from being done because I've only described the feasibility of doing this in a small number of instances. We're going to have to do this on a regular basis for most of the important machines and the important applications and operating systems that keep evolving over time. If we don't do that, then we will lose access to many of the objects that have been created in those contexts. So there's, again, I don't want to go too deeply into this because it's excessively detailed, but I want you to appreciate that there are so many different little bits and pieces that we have to get right in order to make this system actually work. Again, I have to say that having to emulate hardware bugs in addition to making the hardware work the way it was supposed to was one of those little surprises that I hadn't anticipated that they told me about. So I was thinking, if we were really going to tackle this problem successfully, and maybe 10, 15, 20 years in the future, what would I point to as a successful solution to the digital preservation of our objects that we create? And so one of them is obviously the means to capture the digital content and then move it from one storage medium to another. And some of us do this today. I mean, we take things off of our current computers, our laptops, onto memory sticks, for example, and then we load them into the new computer that we just got. And we do this with CD-ROMs, we do this moving them into DVDs, we move them into Blu-ray, we move them into other hard disk formats as these things evolve over time. So we have to have a means of copying bits into the new media. We also have to have, if we're going to retain these digital objects that we've created, we have to get the metadata as well. So we have to have rules for that. What metadata should we capture? What is the norm? And what can we anticipate that the archives will insist on as they ingest our digital content into their systems? We have to figure out how to make sure that the preservation authorities, whether it's the libraries or the archives or other institutions, have the rights not only to hold the data, especially executable data, but they have the rights to let others execute that data. So we have to have a kind of preservation authority which gives rights to the archives that they wouldn't otherwise have. We might need legislation that says it's okay for an archive to share the execution of a piece of code that otherwise wouldn't be permitted for the purposes of preservation, for the purposes of future access to that data. Copyright materials have interesting properties because copyrights and patents eventually expire. And so if you're part of an archive, you may ingest material that's still copyright or that's under patent, and you have to keep track of when it is okay for you to share that information and the use of it with a third party. And so we have to make sure we know those dates and we know when it's legal to allow others to have access to that executable material. There's also an interesting question about maintaining the integrity of the content. The thing that you don't want to have happen is that you have all of these digital objects you've created, whether it's pictures or videos or files of text and so on. If you store it away in the archive, you want to make sure that it hasn't been altered either by accident or deliberately. So we have to have a way of digitally signing these digital objects to make sure that they haven't been modified. And so again, technology of digital signatures and hash coding are required in order to achieve that objective. So you can begin to see some of the practices that a digital archive might have to institute and some of the technologies that they might have to implement. There's also a significant question about developing a business model that will allow the process of storing information away and making it accessible again can be supported over long periods of time. And I have to admit, I have been thinking in terms of hundreds of years in concert with some of the other digital objects, or not digital, but other written objects that I talked about at the beginning, like the clay tablets, for example, or the vellum manuscripts, we're talking hundreds of thousands or thousands of years. And I was trying to think of which organizations last a long time. And the ones that immediately came to mind were breweries, some of which are hundreds of years old, or vineyards, which might be in the same family for hundreds of years, or the Catholic Church, who's been around for 2,000 years and had a role to play in preserving information by having the monks copying manuscripts, or even maybe banks. But I couldn't figure out exactly the relationship between a brewery and digital preservation. All I know is we have the longevity part, but it wasn't clear, do we put the digital information in the beer bottles? I'm not quite clear what should we put it in the DNA and the yeast of the beer? So all I have right now is the notion that there are some organizations whose business models give them long-lasting life. And the question is that the business model I need for a digital archive? Now, there is an organization that just got started. It's literally in the UK in its primary test period called eMortal. And they basically are saying, you take life insurance because you want to have a legacy for your family. So the idea that he had, the founder had, is that the life insurance companies could sell data insurance as well as life insurance. And so you could buy a policy that will capture and hold your data in some archive in addition to the life insurance that you buy. And the idea would be that, by the way, you know what the business model for life insurance is? You keep paying until you're dead. I don't know of any other product that has that property. But so the idea is you just keep paying until you're dead, and then all of your data is available for your descendants. So I don't know if this business model is going to work, but it's one of the more clever ones that I've encountered that tries to take advantage of another business model, which seems to have succeeded pretty well. I think the other thing which I think is very important, some people will say, well, it really isn't worth saving everything. And I have to admit, looking at some of the Twitter sphere, I have to agree with that. On the other hand, there might be something that you think is important to save because you see that it's valuable for your family, for your descendants. You think it might have historical value. And so if you wanted to save something, you should have the opportunity to do it. You should have an option. You should have a place to go and a technology to turn to if you think something is worth saving. Now, I have to admit to you, I've had these conversations, and at one point I remember being in a room with about 50 librarians talking about long-term preservation. And in the midst of the conversation, some young kid got up and said, well, this isn't really a problem. The important stuff will get copied into new media, and the stuff that wasn't important won't, and nobody will care. It took me half an hour to get the librarians off the ceiling. And the reason should be pretty apparent to you. They know that sometimes there are little letters and notes or other things, artifacts, whose importance in history isn't understood for a couple of hundred years. When a particular document is suddenly unearthed that explains a decision that was made 200 years before, they recognize that this preservation was important. And of course, they also all agreed that preservation by accident wasn't the plan. So this whole process and this whole problem deserves a lot of attention. Now, I will tell you that this problem is not unknown to quite a number of people in the world, and organizations have formed around trying to find solutions to it. And I thought I would share with you some of those so that you know that a lot is going on, although it tends not to be terribly well coordinated. These folks often know each other, but finding a way to make all of their efforts more coherent is a really tough challenge. And in some ways, for me personally, this is very much like the challenge of getting the internet to work. At the time that Bob Kahn and I were doing this design work, there were computer networks in existence that linked computers together, but frequently they were computers of the same brand. So IBM had SNA and Digital had DECnet, and Hewlett-Packard had DS. And these didn't interwork with each other. And so it's sort of like, imagine now a bunch of different archives that have captured information, they've stored it away. You can go to that archive to get this particular information. But if you wanted to move this data to another archive, it might not work because they don't have common standards. If an archive goes out of business, you'd like to have the ability to move the data to another archive. And so you want to have standards and norms in which the archives can interwork. So there is an internet archive run by Brewster Kahle out in San Francisco. His job for almost 20 years now has been to crawl through the web, just like Google does to build its index that you use to search. And Brewster captures the web pages and stores them away. Now, it turns out this is not as simple as it sounds, because those web pages have URLs in them. And if you can just copy the web pages and later pull them up and then click on the URL, if it's 50 years from now, the URL may not resolve to anything because it's gone from the net. In fact, some people have pointed out the internet has a couple of odd properties. The first thing is it remembers stuff that you wish it didn't. And the other thing is it forgets stuff you wish it remembered. And so Brewster is trying to remember as much as possible, but he actually has to alter the web pages. So when he takes them into his system, all the little URLs that point out into the big World Wide Web have to be resolved into local links inside his archive. So when somebody clicks on the URL 20 or 30 years from now, it resolves to something he's already captured. And so this is actually a mechanically important process. He's ingesting not only web content now, but he's actually got books and software and other kinds of content that he's accumulating in the digital archive. He even has a backup site. It's in the Library of Alexandria in Egypt. I mean, I can't think of anything more iconic than having a backup site at the Library of Alexandria. You remember that the libraries of Alexandria burned down twice. And the third one wasn't built until 20 years ago by my very good friend Ismail Serageldin, who just recently stepped down as the director of the Library of Alexandria. It's a beautiful $50 million archive sitting on the site of the original Alexandria Library. But it has a lot of modern equipment in it, and as I say, it backs up Brewster's operation. There's a computer history museum out in California in Mountain View, not far from Google headquarters, and they are ingesting all kinds of hardware, all kinds of software, some of which is still running, most of which is not, but they're collecting historical items and artifacts and documentation and everything else. Google has started a project some time ago to scan books that are part of libraries that are in hard copy form in order to make them more accessible online. Some of those books that are scanned are still under copyright, and so Google can't release the full text. But we do release bits and pieces in accordance with the copyright owner's instructions and little snippets just to give you a sense for whether that book has content in it that you care about. There's also an organization called the Cultural Institute, which Google started. It's in Paris, France, and it has been going around with the permission of museums around the world, scanning at high resolution all kinds of artifacts and paintings and the like in those museums in order to capture those in an online form. Now, once again, remember, I talked about digital dark age and the concern about preserving digital content. Everything that we're doing at Google is creating digital content, and now the question is, will it last? And so one of the challenges that I put before the company is, are you sure that in the digitizing of all this stuff that you've given serious thought to how to preserve it for hundreds of years? And this continues to be a discussion that's going on. I mentioned the digital object architecture that Bob Kahn and his colleagues have developed. That's now being used for long-term preservation of references to digital objects. The Consultative Committee on Space Data Systems, which establishes standards for space communication, has developed an open archival information system architecture. And in the audience is Kevin Gifford, who is part of that effort. And I want to acknowledge that this is a very important thing for preservation of space information. And you can see from the earlier anecdote about the loss of the image satellite and the desperate need for an old 4-millimeter reader, you can see how important it would be to have archival standards. And so this overly busy slide, which is there just to tell you that there's real substance behind what it is that the CCSDS is trying to do. They're trying to create a set of rules that will allow multiple archives to exist and still to interwork with each other. And this is a very important initiative, important for the preservation of space information, but equally important as a generalization for the preservation of other digital content that you and I might be particularly concerned about. There is another organization called Rhizome at the University of Freiburg. They're preserving a very interesting kind of artifact. There's a lot of art which is actually produced using digital programs. Some of you will see these on your laptop. Sometimes it's a projection system in the side of a museum. Often these artifacts are ephemeral in the sense that you never see the same thing twice. What Rhizome is trying to do is to preserve the ability to keep rendering those artistic objects over significant periods of time. And in order to do that, sometimes they have to try to build new hardware that will emulate the old hardware or to try to keep the old hardware running. And so their purpose is to keep the software and the hardware which is producing these artistic things in functional form so we don't lose access to that particular artistic rendering. There's another effort which is, I think it was tongue-in-cheek, is Interplanetary File System. This is actually a distributed file storage system using hash coding as a way of capturing digital content and distributing it in a fairly large architecture and being able to find it again and to pull it back out. And so again, their objective is to maintain this digital storage system over long periods of time. There's even an organization called the International Internet Preservation Consortium. The last time we met was in Iceland, and there were about 400 different people who showed up representing a number of different organizations, also concerned with trying to establish standards and interoperability for archives of this kind of digital data. In the UK, there's a depository libraries program which is run by the British Library, and there are participants of libraries, including the Bodleian, for example, at Oxford. I'd recently run into a project which is in the open source space called Perkeep, used to be called Camlistore, and it too is another distributed architecture which aims at storing information away and recovering it, including the ability to essentially execute old software. And finally, the thing that I was surprised to learn about today is the Media Archaeology Laboratory that's here at the University of Colorado. I wandered in at the invitation of Laurie Emerson, who may be here in the audience somewhere. I want to thank Laurie for allowing me to spend 3 hours walking through history. I mean, it was like walking into a time machine to walk into the basement of the building where she is. She has old computers going all the way back to the 1980s, early 1980s. A lot of these are Apple IIes, Apple II Pluses that are from the late 70s. Some of them are Macintoshes. Some of them are IBM type machines, IBM PCs. And all of them were operatable. They were literally operationable. And the stunning thing was that Laurie was actually able to run them right there. She knew how to turn them on, turn them off, actually run some of the old software. It's astonishing, especially given that she's an English major. And so this tells you something about, the sort of scope of capacity. She sort of fell into this, and I'll let her tell her story, but she fell into this because she discovered a poet who was writing poetry using a computer to demonstrate, to essentially present the poetry in an online and interesting and dynamic way. But this was very impressive because she has 5¼ inch floppy disk readers, 3½ inch floppy disk readers, which are still functional. Now, I have a personal experience recently. I had a bunch of 3½ inch floppy disks, which I wondered, what was on them. And I didn't have any readers, so I went out on eBay and I bought a 3¼ inch floppy disk reader that had a USB port that I could plug into my Macintosh. I plugged it in, And I put in the 3.5-inch floppy disk, and it actually pulled files off the disk. I could see them in the directory. They were all WordPerfect programs, or WordPerfect files, and I didn't have a WordPerfect processor application program to run them. Now, there are people who've heard this speech before, and they say, go on Google and you search for, WordPerfect conversion, and you'll find somebody out there on the net that'll do the conversions for you. So that may solve some of our problem, that we will have people who are willingly putting source code into places like GitHub or SourceForge, or who are offering services online on the internet. But again, this is sort of haphazard. It's not done with a real interoperable long-term plan in mind. And so my last point, again, is that we have this problem. Our information will disappear if we don't take an action to preserve it. And we have to solve the three legs of the stool. We have to have the technology to preserve the bits and make them interpretable. We have to have a business model that sustains that over long periods of time. And we have to have the legal framework in which preservation actions are given authority in order to allow this kind of thing to take place. So I'll stop there. I will thank you all very much for your attention, and I am happy to try to respond to questions, which, by the way, don't have to be just on this topic, but can be on other topics of your choice. Thank you very much.
Hello.
Hi.
My name is Nicholas. Thank you for the excellent talk. Very informative, and it's something that I think all of us can relate to, finding information going missing or something that we want deleted to actually be deleted from the internet. I'm wondering, in your opinion, how long will we be in the era of digital media? If you look at how long physical media existed, people couldn't have probably never conceived of digital media and thought everything had to be preserved in a physical form. How long do you think digital will last until we come up with something even beyond it?
Well, I don't have an idea what goes after digital. And I will tell you in a kind of retrograde way, when people ask, what should I do about my digital photographs? I tell them, if you really want to save those photographs, print them out on high quality photographic paper, because we know that that photographic paper could last 150 years at least. We have demonstrations of that. What we don't have is demonstrations of digital media lasting more than a few decades at most. So I really hope that the problem will be resolved, but my guess is that we are going to continue to use digital media. It's too powerful and too valuable to abandon. Our ability to take digital content and do things with it that we could not do with the other media is too compelling. But these digital media are going to change over time as we discover how to do more, higher density, faster storage and retrieval and the like, maybe even faster indexing. So I think that digital is going to be with us for a very long time. There is one potential storage medium which is sort of digital, but it's biological, and that's using DNA. Now, this is not the DNA that nature produces. This is the deoxyribonucleic acid that we generate the codons for. And we use the codons in this DNA to encode digital content. And this is not DNA that you would expect to be alive or anything like that. It's DNA that's simply using the complex molecule as a recording structure. There are some demonstrations of this that have taken place in the UK. DNA has a very interesting property that once you essentially remove all the water from it, it has very, very long lifetime. And you've seen that happen when people have taken DNA from old dinosaurs and things like that and resequenced it. So that might be one kind of storage medium, but it's still digital. And there's also a little problem. I said, so how hard is it to generate this sequence that you want? And it said, well, it's time consuming and expensive. So at the moment, this is not a solution for us.
Thank you.
Hi, I'm CJ Herman with the Interdisciplinary Telecom Program here on campus. And you noted that in order to preserve applications, we need to preserve the environment
That's
that
right.
they execute in. Do you feel like the current ubiquity of cloud applications complicates that? Now, instead of having to keep track of state of one system, we have to keep track of state of multiple related systems. It seems exponentially harder to me to accomplish
I
that.
think you're really right about that. I don't honestly see a way of taking the technique that CMU used to replicate the environment in a single computer and literally capture the state of the cloud or the portion of the cloud that's being used to render some particular service or some application, which is why in the case of the cloud, it's necessary to have an export format that you can capture, in which you can use these particular techniques. And so this gets us back to this question of how, what goes into the cloud, what comes out of the cloud. And I have to admit to you, this is a little tricky for me because it's the first thing you don't do when you walk into the senior management at Google is to say, let me talk to you about the possibility that Google will go out of business. This is not a good way to start the conversation. And yet I worry that the cloud world, which is built up around particular business models, might someday morph into something which isn't like it is today, and that it won't sustain all of the content that we currently leave in the cloud thinking it's going to be there forever. And so your point is extremely well taken, that the properties of the objects in the cloud may not be totally preservable. Example, in the case of a document in the Google system, the Google Docs system, those documents are literally scattered across the cloud systems. It's not just one file in one place. We do that in order to preserve the data. We replicate these pieces across our entire set of platforms, multiple data centers and the like. When you're interacting with that, it looks like there is just one document somewhere and multiple people are allowed to make changes to the document at the same time. Sounds crazy, but it turns out to be incredibly useful if you're having a video conference, trying to work together to get a document finished, the ability to write in different parts of the document at the same time, or change elements of the spreadsheet, or argue over a particular content. You type something and the other guy says, that's dumb, and he types something else. It's all happening in real time. I've been writing a paper on digital preservation with Richard Ovenden, who is the director of the Bodleian Library at Oxford. We were sitting across the breakfast table for about 3 hours, each of us with our laptops open on the same document in Google Docs, and we would type different sections independently, and then we would direct each other to what we had typed, and then we'd argue across the table about, no, that's terrible, try this text. And after about 3 hours, we got quite a long ways, and then I realized he could have been in Oxford, and I could have been in Washington, D.C. doing exactly the same thing, because we could have been using a video conferencing tool. You can't replicate that with anything other than the cloud system that it's part of. So we could pull the document out and make it look like a Microsoft Word document or .txt or something else, but we couldn't replicate all of that functionality. So your point's spot on, which is why I keep talking about having the ability to extract this stuff with all the metadata that's needed. So thank you for that question.
Thank you.
Let's go to the next microphone.
Yeah, my name is Manny here. I work for Alltech here at CU Boulder. Building on the question you just answered, do you think then there is a role the blockchain technologies now, of making a difference in preservation?
So thank you for not asking if Bitcoin is going to pay for all this. So blockchain is simply an interesting distributed ledger. It doesn't necessarily have any particular beneficial properties when it comes to preservation over time. It's not even clear, frankly, that there are business models that will make blockchain implementation sustainable over long periods of time. This is not the right place to have a big argument about blockchain, but here's the important thing. Blockchains are currently being used to capture a transaction that has taken place in such a way that it's not possible for some other party to change the transaction. So it's good for storing a record of something that happened at a particular time and place, for example, in an immutable memory. But the object that might be part of the transaction is not part of the blockchain itself. The object is sitting someplace else and is referred to by the blockchain. So there isn't any preservation value given or benefit given by having put the transaction reference in the blockchain. The object itself is still at risk if it can't be preserved in the medium that it's been stored away. And in fact, just to give you a Bitcoin example of that, Bitcoin uses blockchain, and people store the money associated with the transactions in wallets that are not part of the blockchain. If the wallet is not well protected and somebody manages to break into the wallet and steal the Bitcoins, the fact that the transaction is recorded for all time doesn't help because somebody has absconded with the value. And there are instances reported of things like that. Some of you are nodding your heads. Mt. Gox, for example, 400,000 Bitcoins, poof, gone. Of course, personally, I don't think Bitcoins are worth anything anyway, so I don't, I'm sorry, you didn't ask about Bitcoins, and I'm off on this rant. I apologize for that. But listen, run the other way. It's a commodity. It's like taking payment in pork bellies. So it's a commodity, and it's treated that way by the Chicago Board of Exchange. So, be very careful about people selling you Bitcoins or even overselling you blockchains. So, sorry, it's not pixie dust. It's not magic. Okay, next question.
Can we beam the bits to Mars or other planets?
Well, you'll have to talk to Elon Musk about that. Yes, sir.
So in the world of trying to preserve software, old machines, some of the protections that companies put in place, like activation of licenses, becomes a problem when those activation servers goes away. So how do we prevent the inability to have Windows 7 work for us in 40 years?
Yeah. So, this is a really, it's called a portmanteau question, right? There's a whole bunch of pieces to it. Anytime you introduce access control, you introduce something else called a denial of service attack. It's when you use cryptography and you have to remember the keys, or when you use passwords and you have to remember the passwords, and then you forget them, and now you can't get in because you were trying to protect it from other people getting in. Now you can't get in either because you don't remember the password. And so we resort to a variety of bad practices, like using password as our password because that's easy to remember, or writing it down on a Post-it and sticking it on your laptop, or keeping a piece of paper in your pocket or your wallet. We invent a variety of different things to cope with the problem you describe. I'm going to suggest to you that a part of this question of access control and the ability to enforce it may actually suggest, remember the preservation privileges that I kind of alluded to in my talk? We may have to give some authorities to the preservation archives that they wouldn't ordinarily have, like the ability to get access to things possibly under the right conditions, showing the right bona fides, which, by the way, as long as I'm wandering down this path, let me suggest to you one of the conundrums that I don't have a good answer to. Suppose that you have accumulated information that you care about, family photos, important documents, historical information, and you put it away in the archive. And now you have to decide who should have access to it and when. And you might have categorical information like the public cannot have access to this for 100 years or 50 years. Or you might say only family members can have access to this, although the definition of family member now has to be determined somehow. A family member would have to establish bona fides. You don't have the ability to say which family members, especially if they haven't been born yet, And so we have a vocabulary problem trying to explain to the archive how to protect the information and make access to it only to the parties, as yet unknown, and under what conditions. And so it's a messy process to cope with the problem you're describing. So we will have to find tactics that will let us identify legitimate parties. And in some cases, it might be, patent rights that limit access for a period of time, or copyrights that limit access, or personal preference that limits access, or maybe even national policy. So think about the presidential archives that are often contain classified information. There are rules about when things become declassified, and sometimes it could be for many years. Sometimes it could be the decision of the president to decide that it can be declassified, not recalling any recent examples of that. So, that's not a really great answer to your question because it's such a hard problem. And figuring out ways to make it less hard are very important, but it will remain a tricky area for us to cope with. Yes, sir.
Synchronize.
I'm sorry, I didn't understand.
Sorry, a bad TCP joke.
Oh, okay. Sorry about that.
I'm curious about the notion of using DNS and the fact that it's unstable.
Mm-hmm.
There's an interesting conundrum in that space of naming things, where it's hard to produce a naming system that's both unique, human readable or human rememberable, and decentralized. You might know it as Zuko's triangle. Could you elaborate a little bit more on that? How we can type google.com without having to remember what the IP address is? Thanks.
Okay, so first of all, we would not want to use an IP address as a permanent identifier because they keep changing as they should. It's a very low level indication of a termination point in the net. The problem that I've run into in the domain name system is that the strings are names. They are, or something. They are strings of characters. And people care about the meaning of the characters and who owns them or who has the right to use them. And it's an incredibly intense space. For example, Amazon is a top-level domain now in the ICANN system. And there's disputes over who is allowed to use the .amazon top-level domain. Is it the company, or is it all the countries that are surrounding the Amazon River, or something else? So if I were going for something which had long-term stability, I would not choose characters, strings of characters that have any meaning at all. I would much rather have strings of numbers. Of course, nobody can remember strings of numbers. And so we'd have to build a system that lets you associate something you can remember with the number which nobody should care very much about. I don't care if it's 673122 or 51708. Those are just nondescript identifiers which we would apply and assign permanently. But this is a huge area of debate and controversy, especially once these strings have value. And so the problem is things that have value become things worth fighting over, and people fight over them. So business models in this space turn out to be not only important and necessary, but also a source of enormous amount of conflict. And so I don't have a perfect answer for you, except that the digital object identifier system that Bob Kahn uses, is essentially mostly strings of digits that don't have any particular deep semantic meaning. And that removes at least one layer of controversy over the identifiers. Okay, question over here.
So if you're in line now, we'll try to get to you. So go ahead, stage right.
Yeah, Mark Arnold. Switching gears a little bit, I'd like to ask you a more personal question of sorts. I was in what was then called data processing before IT.
Oh yeah, that's the old term for what programmers do.
Exactly. And when TCP/IP came out, I viewed it then as just being one of I don't know, dozens of different protocols.
Yeah, well,
and
it
really,
was.
It really was, and it was not that special. It didn't strike me as a user as being that special.
No, that's fair.
But
that's very fair.
time has now shown us that it has had an absolutely remarkable global effect in terms of, industry and communication and on and on and on. So I'm just kind of curious, was there any point at which that stands out in your memory as being kind of an epiphany where you realized that TCP/IP was in the knee of some massive curve, and that it was actually now taking off, and that the reach and the scope of it was going to be so dramatically different from other communication protocols at the time? Because it certainly struck me as being something of a surprise.
Yet another protocol. Well, of course, we knew right away in 1973 that this was really going to be a world-shaking thing. The honest answer is that this was an experiment, first of all. And so from 1973 to 1983, we are using this protocol as the part of the creation of an experiment to figure out whether we could connect multiple packet switch nets to each other of highly different varieties, different media, satellite, radio, optical fiber. And so this was purely an experiment. In 1983, we turned the system on after having spent 5 years implementing the TCP/IP protocols on a bunch of different operating systems. But it's still largely an experiment, although it goes operational after 10 years of work for the academic community and for the military. And it stays in this academic environment. It's being used especially by the National Science Foundation in the mid-1980s to connect 3,000 research universities around the United States. And it begins to spread outside to other countries in their research and education networks. NSF sponsored a lot of that by funding connections from the US complex of networks into foreign ones as well. So for quite a long time, this is still very much an academic environment. Software and hardware implementing and using TCP/IP are becoming available during this period. By 1988, you had router companies like Cisco and Proteon and eventually Juniper and others who had hardware and software that was readily available to purchase, so you could build a piece of internet if you wanted to by buying parts of it. I didn't see, and by the way, we were in competition with several different systems. So again, I mentioned earlier, IBM had SNA, Digital had DECnet, Hewlett-Packard had DS, and there was an international initiative by the International Standards Organization called the Open Systems Interconnection Model. Now, just as I was completing the internal standardization of internet in 1978, this Open Systems Interconnection project got launched. And so they designed a whole new suite of layered protocols. And because they were an international standards organization, a lot of governments, including our own, said, well, this TCP/IP stuff is just temporary, it's just academic anyway. We'll all make use of the international standards once they come out. And they were not coming out. They were documented, stacks of documentations, but not much in the way of implementation. So let me give you 2 dates for me that were very significant. The first one is about 1993. At this point, I am now the president of the Internet Society. I have been fighting this OSI battle, governments and the commercial sector, for 15 years. So there's no guarantee yet that TCP is a winner, except that it's being implemented all over the place, and OSI is not. So I finally write to the National Institutes of Standards and Technology, which standardizes government use of protocols, and they had said, we're using OSI, here's the government OSI profile. So as the president of the Internet Society, I wrote and I said, it's time for you to evaluate TCP/IP against OSI. And they assigned a blue ribbon committee, and at the end of a year, they declared that TCP/IP was as good as OSI, and that you could buy that instead of having to purchase OSI for government purposes. And so this is 1993. Guess what else happens in 1993? Mark Andreessen and Eric Bina do the Mosaic browser based on the World Wide Web design that Tim Berners-Lee released in December of '91. That gets everybody's attention. Netscape Communications gets built by Jim Clark, who takes Mark Andreessen out to the West Coast along with Eric Bina and starts Netscape Communications. They launch their project. In 1995, they go public. The stock goes through the roof. The dot boom is on. And so that time frame, the 1993 and 1995 time frames, are the real trigger points. But I will say one other point at which I believe that something big was happening, and that was in 1988. Now remember, for me, this is 15 years into the project. And in 1988, I went to an interop exhibition. This is a place where TCP/IP products and services were demonstrated. And this is at the Moscone Center in San Francisco. There are 50,000 people who show up at this thing. And I walk in with Eric Benamou, the then CEO of 3Com. And I see this 2-story Cisco display. And I turned to Eric and I said, Eric, how much do these displays cost? And he said, $250,000. And he said, that's not counting the cost of the people to man the booth for a week. And my jaw just drops. I'm thinking, my God, some people think they're going to make money out of the internet. And you know, this is amazing. You know, it wasn't my purpose in life. But at that point, I realized that I wanted everybody in the general public to have access to the internet, which meant there had to be a business running internet services. And so in 1988, I began another campaign to allow commercial traffic to flow on the government backbones to demonstrate to the private sector that internet was a real business. And I can tell you, watching the statistics, that the internet took off at that point, and it hasn't stopped.
Well, thank you very much.
You're welcome. Okay, next question over here.
Hi, my name's JR. I wonder a lot about how can we best inspire the spirit of preservation in companies that might have like a financial disincentive to do so themselves. You know, maybe they want to move to a new version that breaks compatibility with something older.
So, it's a good question. And that's why I think that as all of us start worrying about preservation of content, we should sort of demand that there be a regime built around privileges to preserve, that you should be able to say, I want to preserve this, and I want to have a place to go to make that happen. It's like a lot of other legal regimes. When the librarians had to fight to allow fair use of content of books in the library by copying on Xerox machines, that turns out to be an example of the kind of battle that we will have to fight at some point.
Thank you.
And I'm ready for it. Yes, sir.
Hi, my name is Sylvain Guégan. As an IT director, I always being asked the question about storage and capacity. So you presented the concept of data preservation, but you didn't really talk about the dimension of capacity to store the data. And I know that technology evolves very quickly. We're able to store more and more data as the time passes by. But at the same time, I think as you presented, I mean, we are generating more and more digital data. I mean, do you foresee a future where we would generate more data that we'd actually be able to store? I mean, you haven't really spoken to that dimension, I guess, of your.
So I'm not a technologist down in the hardware space, but I will tell you that the rate at which we have been able to increase storage capacities has exceeded the rate at which Moore's Law was running over the past 40 years or so. So the answer is I don't see yet any kind of diminution in our ability to increase the amount of digital content that we can store. The physical sizes of the bits, for example, and the particular media that we use, possibility of multiple layers of storage, are all still before us. Chemical storage, possibility of using molecules, complex molecules as storage media, says to me anyway, that there is a long way to go before we run out of room. Now, I will say that as we get to much higher densities, one of the big problems will be the rate at which you can move bits in and out of the store. Because if it takes you time to find things, that's why you need to have really good indexing systems and hashing systems, so that if you have a high density storage system, you can have an index over here, which is a lot smaller, that lets you say, I need that particular piece of the memory and pull that out without having to serially scan through all of it. So I'm still fairly positive that we are not going to run out of room anytime that I can see, anytime soon.
Thank you.
So we have one last question over here,
I wanna-
and then we'll get the rest of you over here.
I want to follow up on that last question a little bit. You've touched on business models and a number of points in your talk, and these projects up here, they're basically projects.
I'm sorry to interrupt you. I'm not hearing you very clearly, and I'm not sure why, but except for the fact that I wear 2 hearing aids and I'm half deaf, that's part of the problem.
So these preservation projects they seem like passionate projects. Is there a business model, a business motivation, including profit, for doing preservation of digital material?
Well, of course, the simple answer to that would be that you should just pay me to save all your stuff, and I'll find a way to do it. But I don't think that's a really wise option for you. We know that there are institutions that have survived for long periods of time that are part of the information storage business, libraries and archives being examples of that. Universities are long-lived institutions that are known for storing content. Figuring out whether the technology of storage will fit into their business models is still, not exactly clear to me, but you see what they did before. They built big buildings to put books in and manuscripts and maps and so on. We build institutions like the Library of Congress. For a while, they would always get 2 best copies of everything, published. By the way, the Copyright Office in the Library of Congress also got 2 best copies of every design that was done, except they also would get the artifacts. And so the Library of Congress has the world's largest collection of bird baths that are sitting out somewhere in Maryland. They stopped asking for artifacts, and they were happy with designs and things like that. I mean, what do you do with 1 million bird baths? So anyway, I have the feeling that these institutions, we will turn to these institutions and at least expect them to come to grips with this problem, because they've historically done that. But the technology and the business models still have to be worked out. In some cases, those business models are public payment for the storage and preservation of content. The presidential libraries, I don't know actually whether they get any public funds, but they certainly get private funds. So you can see a kind of mix of different sources of financial support to preserve this content over time, depending on who it is that wants to save it. But as I say, this is still not a solved problem. So if you have ideas, we should talk about it. Okay, one more question over here.
Yes, my name is Ted, and I've spent 10 or 15 years looking for a solution to what you have defined here.
Did you find anything?
So I know where you're coming from. In fact, 1.5 years ago, I gave a 10-minute talk of pretty much just what you gave about the history and the need for this to my Toastmasters.
So this
group.
Implicitly, I could have done 10 minutes instead of an hour.
Yes.
Thank you for
In
that.
any case, during the course of this time, I have come up with a plan to solve a chunk of the problems you have defined.
Super.
My question is simple. It's way too complicated to talk about here. My question is simple. After we're done here, could you and I exchange contact information, and I'd like to get a dialogue going.
Sure, absolutely, not a problem.
I'll come see you afterwards.
Okay, and just so everybody else doesn't have to do that, my email address is Vint, V-I-N-T, @google.com. And so if you have ideas, I'm willing to entertain them, but I'll be happy to exchange cards with you. Last question.
So you mentioned about digital preservation and how it's going to become more difficult in the future. How about the reverse of retrieving specific information as it grows much larger?
Can you come closer to the microphone? That'll help me a little bit.
So digital preservation will be difficult. How about retrieval of specific information as it grows larger and larger? Can I hear some of your thoughts about how you can how you might re-envision retrieval of data?
So Google has shown us the way in part because they've had the ability to do full text indexing of the content of the World Wide Web. And so when you're searching for things, in the case of Google, you search for strings, and we try to do matching to discover which web pages have those strings in them. And that's worked, in my view, extremely well. There is, however, a collection of information on the current World Wide Web which is not visible to the indexing and search engines, and that's the content of the databases themselves. So when you have scientific information, for example, or you have other data that is not represented in the HTML format of the World Wide Web, the indexing systems don't even see it. And so this is something that Tim Berners-Lee has been worried about for quite some time. He calls it the deep web. That's not the same as the dark web where all the bad stuff happens. Deep web is, this is like, the universe is 5% real matter and 75% dark energy and, 25% dark matter. We've given labels to these things. We don't know what they are. We have a lot of dark information, if you like, that's not visible in the indexing system. So the question is, how do I characterize the content that isn't visible in the normal indexing process? That's a semantic problem. There is an organization called schema.org, which is trying to synthesize various ways of representing the semantics of content and its structure. And so those tools may turn out to be ways in which we can at least represent data that isn't otherwise indexable. And in theory, that will help us find it. The other thing which has been interesting in the recent past has been the use of machine learning in order to do image retrieval and to do audio retrieval. So if you whistle a tune and we try to figure out what it is. So I see increasing amounts of effort to go into the indexing of non-textual information. And that gets to at least part of the problem that you're describing. So I think we will edge our way into solving this, sort of one bit at a time, if you like, no pun intended. But it's not a trivial problem.
Thank you.
Oh, we have another question. Hello there.
Last question, please.
I had a question about medical health records, and I'm in the imaging field in ultrasound, and so that ties in with your imagery thing. But do you see anything different about how if medical records are stored on a chip on someone's skin or under their skin, or however that would be also transferred transgenerationally?
Wow.
Also because the history of their medical care is significant to their legacy, their families.
That's actually a really interesting idea. Let me give you a parallel example of this. And you buy a car in the 21st century, and the car has all kinds of components in it, and you want to keep a record of all of its service, and you have the ability to instrument the car. You're capturing data about the car's function and operation. You go into the shop and they plug in a little plug and they pull all that data out. You can imagine accumulating all that information about that car and using it for diagnostic purposes. It's easy to imagine what you just described, where we take all this medical information about our bodily functions and we capture that. I don't know whether we need to keep it in a chip under our skin necessarily, but it needs to be somewhere. And if we wish to do so, we could choose to make that information available to our descendants. And we're seeing a little tiny bit of that now in a funny way with 23andMe, where you take your DNA and they analyze it and they try to tell you something about, well, where did you come from? What region of the world are you in? And you share that information with your kids, or they discover certain DNA sequences that might not be so good, like, APO4E or something, which has to do with Alzheimer's. And you share that information with your kids. So I can actually see doing something like what you're suggesting. I'm not sure we have to put it in the chip under our skin, but we might have to put it in an archive which is preserved for long periods of time and for which access control is carefully done so that the information gets to the parties we wish it to get to and not to others. But it's a really intriguing idea to hand down your family medical history along with your family social history. And so I hope you actually succeed in convincing people to try to do that, since it might benefit your descendants significantly to know how did their ancestors function medically speaking.
I just thought it was interesting because if it's contained on you, there's no way, unless when you die, they remove it, that it's, accessible to others. It's very secure.
Yeah, well, I don't know how secure it is. Also, there's a little issue about how do you read it. And, if it's something you could read through your skin, using, some radiometric thing, that might not be as secure as you would like. I'm not sure I want my medical history carried around in a way that could be read by somebody by just sticking my hand into a cuff and reading the data. Sort of like, having a wallet with what's called NFC field reading capability or Bluetooth. You turn your mobile on, you turn Bluetooth on because it's handy, and somebody walks by and sucks everything out of your mobile phone. So you should think a little carefully about that. But the basic idea of having the information and making it available would be terrific, not only from the family point of view, but think about making that information available in a non-attributable way for purposes of analysis of how is the health of the population, what problems are we seeing. So thank you for that idea. I appreciate that. Mr. Chairman, I think...
Okay, so Vint will be giving a talk tomorrow morning at 8:45 in the Silicon Flatiron Center in the Wolf Law Building. So for that reason, we need to thank him now so he can actually get some sleep.
Thank you very much. Thank you.
Thank you all. Thank you all once again for your support for the George Gamow Memorial Lecture Series.